In this video, we're going to learn how to model and solve forced damp motion in a mass spring system. We'll start by deriving the differential equation that describes the motion when both damping and an external force are present, and talk about the form of the solution and how it's made up of two parts, a transient solution and a steady state solution. We'll then work through an example so that you can see how to solve the equation and interpret the behavior of the system. Let's get started. Let's begin by deriving the differential equation for a mass spring system with damping and external forcing. Down here in our graph, we have a mass M that is attached to a spring and a dashpot. The dashpot is what provides the damping. The forces on the mass are the forces due to the spring and the dashpot, as well as an external forcing function. The force due to the spring is equal to minus kx, where k is the spring constant, and then the force due to the dashpot is equal to minus c times dx dt, that's the velocity, and then c is the damping constant. The other force acting on the system is the external force, and we're going to say for now that that is equal to f of t. Newton's second law of motion states that the net force acting on an object equals its mass times its acceleration. The net force that's acting on the mass in our system is due to the spring, the dashpot, and the external force. That's these terms right here. And that net force is equal to the mass times the acceleration, where the acceleration is just the second derivative. When we substitute in the second derivative for the acceleration and change these terms around just a little bit, we get the equation for forced damped motion. We're going to look at a solution for this equation where the external force is oscillatory and equal to a sine function or a cosine function. The solution to our differential equation is x of t, and it's made up of two pieces. The first piece is called the transient solution, and it oscillates at damped natural frequency beta. You can see that frequency right here in the sine and cosine functions. And because of this exponential term right here, this transient solution decays to zero. The other piece of the solution is called the steady state solution. It oscillates at forcing frequency omega. There's the omega in the solution, and notice that the forcing function has that frequency too. The steady state solution oscillates at this forcing frequency omega, and if we take the limit as t goes to infinity of our solution, x of t, we see that it's equal to this steady state solution. Before we go on to our example, let's make sure we understand the main idea. The main idea is that damping removes the transient motion, and eventually the system oscillates only at the frequency of the external force. Let's now walk through an example of a mass spring system with oscillatory forced damping. In our system, we have a 1 kilogram mass that is attached to a spring with a constant K equal to 5 newtons per meter. There's also a damping force that is proportional to velocity that acts on the system, and it has a damping constant C equal to 2 newtons times seconds divided by meters. There is an external force F of t that's equal to 5 cosine 3t that's applied to the system. We're told that the mass is released from rest at the equilibrium position. We're going to let x of t denote the displacement from equilibrium, and we're going to measure that in meters. We're going to find and solve the equation of motion. Notice in our diagram that the mass m begins at the equilibrium position x is equal to 0, and it has three forces acting on it. the force due to the spring, the force due to the dashpot or damping, and the external force. We're going to begin by writing down the equation of motion. The equation of motion is m d squared x dt squared plus c times dx dt plus k times x is equal to our forcing function, which we'll call f of t. Our problem told us that the mass m is 1 kilogram, and our damping constant c is equal to 2 newtons times seconds divided by meters, and then k, the spring constant, is equal to 5 newtons per meter. Let's also write down our initial conditions. Since the mass starts at the equilibrium position, we can say that x of 0 is equal to 0, and because it's released from rest, that means there's no initial velocity, so we can say that dx dt at time 0 is equal to 0. To make it easier, let's go ahead and let's put these constants back up into our equation. This gives us d squared x dt squared plus 2 dx dt plus 5x is equal to our forcing function, and we were told that our forcing function is equal to 5 cosine of 3t. I'm going to go ahead and highlight this equation and our initial conditions because that's the equation that we're going to be solving. This equation is a non-homogeneous second-order ordinary differential equation, and the solution is made up of two pieces. The solution to this is x of t, and it's going to be equal to the homogeneous solution, notated by x sub h of t, or you could notate it as x sub c of t, plus the particular solution. The first thing that we want to do is we want to find the homogeneous solution, x sub h of t. To do that, we are going to solve the homogeneous equation, and that's the second derivative of x with respect to time plus 2 dx dt plus 5x is equal to 0. The general form of the solution to this equation is x is equal to e to the rt. This gives us the characteristic equation r squared plus 2r plus 5 is equal to 0. We can find r using the quadratic formula, and we get r is equal to negative b, so that's minus 2, plus or minus the square root of b squared, and that's 4, minus 4 times 1 times 5, all divided by 2. This is minus 2 plus or minus the square root. 4 minus 20, that's a minus 16, and we divide that by 2. The square root of minus 16 is 4i. We can divide everything by 2, and we end up with minus 1 plus or minus 2 times I. This gives us the homogeneous solution x sub h of t is equal to e to the minus t, that comes from this term right there, times c1 cosine 2t. The 2 comes from that term, and then we add c2 sine 2t. I'm going to highlight that because we're going to come back to that in just a few minutes. Now let's find the particular solution. The particular solution is one solution to the non-homogeneous equation. So let's go ahead and we're going to write down this equation. Our right-hand side was 5 cosine 3t. I am going to use the method of undetermined coefficients to find the particular solution. I think that's the easiest one to use in this case. And because we have a cosine function on the right-hand side, we can say that our particular solution, x sub p, is going to look like this. It's going to be a times cosine 3t plus b times sine 3t. I have a video on the method of undetermined coefficients if you need to review that. Now we have to take two derivatives. dx sub p dt is equal to minus 3a sine 3t plus 3b cosine 3t. Now we'll take another one. The second derivative is equal to minus 9a cosine 3t. Those 3's are just coming from using the chain rule. And then minus 9b sine 3t. Now we can substitute all of this into our equation, and we have a minus 9a cosine 3t minus 9b sine 3t. And then we have 2 times our first derivative, so this gives us a minus 6a sine 3t plus 6b cosine 3t. And then we just have 5 times x, so that gives us a 5a cosine 3t plus 5b sine 3t. And all of this is equal to 5 cosine 3t. Let's highlight all the constants that multiply cosine 3t. That's minus 9a plus 6b plus 5a. So that's going to equal 5. And then our constants that multiply our sine function are going to equal 0. This gives us minus 9a plus 6b plus 5a is equal to 5, and then minus 9b minus 6a plus 5b is equal to 0. This gives us the two equations, minus 4a plus 6b is equal to 5, and then minus 6a minus 4b is equal to 0. I'm not going to go through this solution. It's just two equations and two unknowns. And when you solve that, you end up with a is equal to minus 5 over 13, and b is equal to 15 over 26. We can now plug these two constants back up into our particular solution, and we get x sub p of t is equal to minus 5 over 13 cosine 3t plus 15 over 26 sine 3t. I'm going to highlight this, and we'll hold on to that and come back to it in a few minutes. What we want to do next is we want to find the general solution, which is x of t. X of t was our homogeneous solution plus our particular solution. So we can say that x of t is equal to e to the minus t times c1 cosine 2t plus c2 sine 2t. And we're going to add the particular solution onto that, and that is minus 5 over 13 cosine 3t plus 15 over 26 sine 3t. Now all we have to do is find C1 and C2. You always have to wait until you get your particular solution to find these constants. We can find these constants by using our initial conditions, and those conditions were x at 0 is equal to 0 and dx dt at 0 is equal to 0. I am not going to go through the algebra to do that. I've gone through this type of problem before in other videos. And when you work through all the algebra, you end up with C1 equal to 5 over 13 and C2 equal to minus 35 over 52. Now here's one of the most important parts of this video. I want you to understand our solution. Our solution is x of t, and it's made up of our homogeneous solution and our particular solution. Down here, I've graphed the solution. You can see that it's oscillatory and that the amplitude is smaller at the beginning and then grows and then stays the same. Our solution has a transient part, and that's what causes the amplitude of the solution to be smaller at the beginning, because the transient part has a decaying exponential in it, and it's going to force the amplitude to be smaller. And then the solution also has a steady state part, and that's what the solution becomes after the transient part goes away. And that's it. You now know how to model and solve forced damped mass spring systems and understand how the solution separates into transient and steady state motion. You should now be able to work through similar problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.